It's me again. We are going to start on lesson 2. We last left off, I believe, talking about why we should do stuff randomly, and that is to hit on target. Sometimes we might be a little side to side, but our center overall will be the actual mean, right? Remember that. Okay? So that is the first thing. So it doesn't matter if you're doing stuff with percents, or it doesn't matter if you're doing stuff with means. You want to make sure you gather a simple random sample. Okay? All right, well, today we're going to be talking about independence a little bit. But first, talking about large samples. All right? So if I'm going to take a sample, let's see, guys, weigh the differences. I'm going to take a sample. Do I want a large sample, or do I want a small sample? Right? Okay, hopefully you guys are wise enough. The larger the random sample, the better you're going to get, right? You're going to come to that truer average, like flipping a coin, right? If I only flip a coin 10 times, I might not get 50-50, right? But if I flip it 1,000 times, I'm going to be pretty close to getting 50-50, right? Remember, that's that long-term average kind of thing working out. So the more that you do things, the more tighter you get, the closer you get to the actual average. So is it better to sample something size 20, do a sample of size 20, or a sample of size 100? And obviously, if I sample things size 100, I'm going to have a much smaller sampling distribution, right? So they're much more likely to produce an estimate close to the true value perimeter, okay? So, for instance, if this is a sampling distribution, remember with all the ways, so if we took like random samples of 100, notice how wide this curve is. I still have possibilities. I still could get possibilities of values that are out here, right? But if I take 1,000, can I get way out here anymore? It is almost impossible to get a value that would be like 52%, okay? We would have a much tighter normal curve, right? And actually, if you think about this, what happens as I start sampling more and more and more and more? What happens finally when I actually do sample everybody? Well, there's no wiggle at all. If I sample everybody, basically, I'm going to hit the mean, right? I'm going to know the actual mean. Right? If I sample everybody, that curve is not a curve anymore. It's just, right? It's a mean. And so, obviously, if you only sample 2 people, you got a lot of variability. The more and more you sample, the closer you get to that actual mean until you sample everybody and you actually know the true value. So I guess this brings up a good point, right? And this is the part that a lot of people don't understand why we do it. Because you'd think the larger the sample, the better, right? However, there is an issue with collecting a large sample. We're going to talk about that. When is a sample too big? All right. Well, remember in chapter 6, right? We had to have things, remember our bins and our bits? That I stood for independent events, right? And we had to make sure things were independent, otherwise this affects our standard deviation. Our standard deviation formula, remember our standard deviation formula was N, see if you guys can quote it with me, times P times 1 minus P. You guys remember that standard deviation formula? Okay, this only works if I have independent events, if they're indy, right? So, here's the issue. What if I'm collecting samples, whether it be from a population? I'm going to give you a little illustration. What if I'm collecting samples from a bag? I don't want to pull them all out, but I'm going to collect a sample. All right? Imagine a bag of 6 blue, 9 red, and 5 green marbles. All right? Let's say I pull a red one out. Okay, so what's the chances of getting a blue? Well, it's 6 out of 20, right? That's the chances of getting a blue. Now, what about the next time I pull a marble out? Do I still have 6? Let's say I got a blue the first time. now my blues have gone down. I only have a 5 out of 19 chance, right? And the probabilities are slowly changing inside that bag as I keep removing marbles from the bag, right? The probabilities inside the bag change and thus are no longer independent. So, can you imagine if I removed a bunch and let's just say I randomly, on some weird chance, I took out like 4 blues, right? Think of how the probability has changed in that bag for blues now. It's no longer a 6 out of 20. I don't know what a 6 out of 20 is. Right now, it's like a 2 out of 16 chance of getting a blue. Way lower probability. Independency rule has completely gone kabosh. Right? Kabosh. So we have this little rule here, guys. If we're taking and removing things from a population, right, we don't want to change those probabilities too much, right? Right? Because as I slowly remove more and more and more, I'm getting further away from that probability, the actual original probability. So here's what we say. I don't know where we got this from, but basically, we allow you to take out 10% of the population. That still leaves 90% in the bag, right? Okay? If we can take out, again, max of 10%. If we take out more, those probabilities could change drastically depending on the luck of the draw, right? And we will soon end up with things that are so far removed, right? So, we only allow 10%. Now, just to help you illustrate this, because some people have a hard time, okay? So let's say I have a bag of 20 marbles, right? How many marbles should I sample out of the bag? 2, right? 10%, right, of 20 is 2. And by the way, it should be 10% or less. You don't want to get more than 10, because otherwise those probabilities change too much. So, I could sample 2, right? Okay, what about another situation? Let's say, I want to sample, I want to ask some kids, you know, sure, how many people have they dated in the year, right? Or their senior year, how many people have they dated, right? Okay, so I'm going up to seniors. Now, let's say there's 400 seniors, right? Now, as I start pulling them out, you know, maybe the high people, if I randomly get high people, those probabilities of getting more high people are going to get less and less. It's going to get just, it's not independent anymore, right? And so, already, I'm not very good about pulling more out. I don't know if this is making any sense. I feel like I'm just talking in tongues right now. But if my sample size is n of 400, how many people can I max sample? Well, no more than 10%. So my sample size, my little sample size should be no more than 40, right? 40 is my limit. I can do 40 or under, right? Now this gets kind of fun because we have this rule where it's got to be 10% or under, right? And we're going to get to another rule later where it's got to be a certain number and over. So we got to find that, like, here's the max, here's the min, and there's like a little sweet spot right in the middle, which we'll figure out here later on. Okay, so here's the next big rule. All right, here's the next big rule. All right, I don't know if you guys got to fill that out or whatever, but here it is. Okay, 2 more we're going to reveal our independency test. Okay. So, first of all, we had our random test. Make sure we do things randomly. Why? So we hit the mark. Right? We don't want to be off the mark. Otherwise, we look embarrassed. Right? We want to hit the mark, so we want things random. Okay? Next test is the independency test. And here, you need to memorize it. N is less than 10% of big N. So you have to have 10% or less of the population if you want to say that. You could say 10% or less of the population. That's our independency test. Why? So that our standard deviation actually works. Okay? Our standard deviation formula will not work unless it's independent. And already, it's not independent sometimes, right? We're pulling things out and it's, right? But if we stay under 10, we haven't changed the probabilities that much, okay? All right, because we're hoping there's a larger amount, okay? All right, now let's bring up a good question, all right? Do we always have to stay under 10% of the population? For instance, like flipping a coin. How do we stay under 10% of the population? How many times can I flip a coin? Right? Well, I could flip a coin. I mean, you haven't seen my good days, but I could probably flip a coin like 1,000,000 times. No joke. So if I can flip a coin 1,000,000 times, what's 10%? The population, really, 10% of 1,000,000 is 100,000, right? However, if you think about it, flipping a coin, does the first flip change the probability of the second flip? See, flipping a coin is already independent, right? We don't have to run into a problem. There's really, this rule is nullified if it's already independent, right? Okay, what if I picked a marble out of a bag and then I put it back into the bag? Do I have to stay, can I only sample 20 of them now? Well, no, if I keep taking them out and putting them back in, it's independent now, right? Meaning the first doesn't matter with what my second, because the probabilities have stayed the same. So I don't have to stay under that 10% rule if it's independent naturally, right? It's only those cases that we're like, oh, this could affect it, right? Okay, that's when we have to stay under 10% of the rule. Okay, cool. Hopefully you guys got those written down. Notice they're the same so far, right? These two are the same. Doesn't matter if you're working percents or whether you're working with percent problems or mean problems. Independence test is the same. And guess what? Random test is also the same, right? So far you're like, oh, that's really easy. This chapter we got 2 more rules we're going to learn about in 7.2 and 7.3. 2 more rules that are going to blow your mind. And these are going to be different. Okay, so our proportion test is going to be different than our mean test for the one that's going to be still revealed. That's the only thing that's different, though. All right, one thing before I go. I want to show how have they used... Oh, yeah, sorry. I almost forgot. Basically, just kind of an illustration, okay? What would this mean if this is my target, right? And I'm trying to hit this target. Now, this is kind of an illustration, right? This would mean that I have a large sample because it's not very spread out. Remember how large samples makes it very skinny, very accurate, or very small scatter, right? However, I'm so far away from that center. Look at, I'm so far away here that I'm biased, right? I had my thing was not aiming in the right area, right? My sample was biased somehow. Okay, you guys kind of see the analogy? This one is kind of centered around the target, right? So I would say there's no bias here. So let's say no bias present. But what do we notice about the shots? It's scattered, right? So there's no bias, but it has a small sample. Because small samples mean more variability, right? All right. Okay. I don't know if I'm going to get to my World War II illustration. That's too bad. You guys will just have to read about it in World War II. There's some books about World War II out there. This one, notice, this is going to be a small sample because it's so scattered. You notice how scattered it is? So small sample, and it's bias. Right? Because it's not even near the center. So it's off, and it's large. Excuse me. Right into the mic. And then this one. This is what we really want, guys. This guy right here. Large sample, so there's not much variability. And straight shooter. Non-biased sample, right? simple random. Well, guys, hopefully you've learned some stuff here. Have a great day.